Today, I have the pleasure to present Filipa Correia. Filipa is a PhD candidate in human-robot interaction at University of Lisbon, and her research is focused on the group dynamics and teamwork within mixed teams of humans and robots. Today, Filipa is going to talk about the challenge of building group intelligence with humans and robots and her approach and findings along the way. I look forward to know more about the details of this topic. And the floor is yours, Filipa. I will stop sharing my screen.
Thank you so much, Joanna, for your kind introduction. So I should share my screen now. Okay, so welcome everyone. Thank you for coming to my talk. So this talk will be about the work I've been doing in the past 5 years. So it means I'm about to finish my PhD. I'm very happy to be part of Talking Robotics series of talks. And I hope you like my work. And let's discuss it in the end. So the motivation and the plan for this PhD, I'm going to start showing you a video. So this kind of interaction is what motivated me to pursue this PhD. And basically, I think after research, after looking at literature, the novelty of my work lies precisely on the intersection of these two topics, human-robot teamwork and multi-party interactions. So in human-robot teamwork, basically, humans and robots have a shared goal, or at least one goal in common. But in literature, we see that most work is focused on dyadic interactions, so only one robot working together with one human. And at the same time, you have multi-party challenges or multi-party interactions that basically address the challenges of having at least 3 agents. It can be more humans, 2 humans and 1 robot and 2 humans, but starting at 3 agents. So this is where my PhD is. What exactly is a group? So Frizith defines a group as 2 or more individuals who are connected by and within social relationships. And these are the 5 main characteristics of groups: interactions, the goals that each member has, the interdependence, the structure, and cohesion. But most importantly, there's a subtype of groups, which are teams, that is more interesting in my opinion. And Frizith defines it as unified and cohesive group. Basically, a team has the same 5 characteristics, but they are even more emphasized. In particular, the interaction need to be coordinated, as you saw in the video before. Team members have a common goal together, and there's a strong interdependence between them. I will focus, my work has been focused on cohesion. So now you might be wondering, what is cohesion and what is this problem we are trying to address? So I formulated the problem in this way: how can we endow a robotic teammate with social capabilities to improve the cohesive alliance in multi-party setting with humans? And to address this problem, I looked at what cohesion is. And basically, cohesion is a multidimensional construct that can emerge from 5 different dimensions or aspects of cohesion. So first, there's the task cohesion, which emerges from the shared commitment towards a goal. Then you have emotional cohesion, which is the degree of emotional expression towards the group feelings. Then you have social cohesion, which is related to the attractions of group members. The collective cohesion is the degree of belongingness or identification towards the group. And finally, structural cohesion is related with norms, relationships, and roles that link the group members together. So I'm going to present 4 main projects of my thesis. The first one tries to address social cohesion, the second, collective cohesion, the third, emotional cohesion, and the last one, structural cohesion. But I would like to emphasize that all of these projects somehow address at the same time task cohesion, because people were asked to form a team with the robot. So there's this shared commitment towards a common goal, which is task cohesion. So now let's dive into the first project, which was membership preferences and team formation. The research question in this project, this first project, was how do attractions and relationships develop towards robotic teammates? And in particular, what are the traits that people prefer on robotic teammates? And this is related to social cohesion. So I'm going to start to show you a video that explains the methodology we use to address this question.
Bem lançado, isso dificulta-nos o caminho. Sinto qualquer coisa. Ah, é o sabor da vitória. Parabéns, colega, foi um bom jogo. E tivemos adversários à altura.
Outra vez a mesma coisa. Tu não sabes que isso não se faz.
Sim, eu estou a perder. A jogar. Já era a altura de retirarem as cartas.
Estou maluco.
Okay, so one thing I would like to before diving into the results of this user study, I would like to emphasize that the two robots that you just saw were acting fully autonomous. And this was the first time I integrated two robots in the same scenario, which introduced a lot of challenges. This is how the architecture looks like. And also, I would like to mention the fact that the full time of interaction for the 3 sessions in the last study had a total of 45 or 50 minutes, which can be considered kind of a long interaction, yeah, for two fully autonomous robots. So as you saw, for the second user study, people had to play 3 sessions, and they were asked for which robot will you prefer to partner with these 2 times, or in these 2 moments of the study, after the first session and in the end after the third one. So what happened? In the first choice, there was a clear preference for the relationship-driven robot. However, in the last choice, this preference was not clear anymore, and the difference was not significantly different. And we found 2 interesting relationships that might explain this last result. So in the last choice, people that preferred the competitive robot were more competitive than people that preferred the other robot. And also, we found a significant association between the performance of the team and their preferences. So overall, the takeaway message from this study is membership preferences in competitive game contexts seem to be guided by personal characteristics and also by team performance. Additionally, the learning goal theory seems to be a good tool to design social behaviors of robotic teammates in order to foster human-robot teamwork attractions, also known as social cohesion. I would also like to mention a follow-up work we had with the data we collected from the second user study. We did an extensive behavioral analysis using Bale's IPA. So we coded and analyzed the social, emotional, and task-oriented behaviors of people in this study. So now let's see the second project, which was prosociality in human-robot teams. So the main research question was, how do people perceive prosocial and selfish actions of robotic teammates? And here we tried to map into the prosocial and selfish actions 2 different degrees of collective cohesion. So the higher level of collective cohesion was the prosocial or collectivistic actions, while the selfish is less collectivistic and more individualistic. We also wondered if those perceptions were affected by the outcome of the team, and also if that outcome can affect the way people identify with the team or trust that team with robots. So we ran a user study with a team of 3, in this case 2 robots acting fully autonomous and 1 person. And they had to play a collective risk dilemma, which was framed into an entertainment game that we called For the Record. But most importantly, during this game, each player has several decisions, and those decisions are basically forcing them to choose between to cooperate and to defect. And what does this mean? When they cooperate, they are trying to reach faster the common goal instead of the individual goal. And when they defect, they are fostering the individual goal and compromising the common goal. So in this particular game, For the Record, to cooperate means avoiding the team's catastrophe, and to defect means trying to have the highest individual score. So our study had a mixed experimental design. The within subjects variable was the strategy of the robots. So one of the robots was a cooperator or prosocial, which means that robot would always choose to cooperate in the game actions. and the other robot was a defector. So it was always choosing to defect in the game actions. We also had another between subjects variable, which was the outcome of the game. So we controlled these, and half of our sample end up as a winning team. So the team won the game, and the other half lost the game. The team lost. So I'm going to show you just a little bit of how the interaction looks like.
Vou pôr ponto no marketing. Prefiro melhorar o meu instrumento. Eu estou a jogar.
Assim eu não posso apostar no marketing.
Marketing means defecting.
Somei 10 pontos.
Ana Gline. Isto deve ser mais positivo. 8! Yeah!
Okay, so the results. Overall, the cooperator or pro-social robot was rated with higher levels of warmth and less discomfort, and this was regardless of the outcome. However, for competence, we found an interesting interaction effect that basically reflects that in the losing condition, the difference, the competence attributed to a defector and to a cooperator was more salient. That difference was emphasized. In terms of group measures, winning the game had a positive impact on the identification with the team, but we did not find any difference on trust. And again, we had a question about their preference between these two robots for a hypothetical future game. And we saw the same pattern as in competence, that the difference is more salient when they lost the game, with almost everyone preferring the cooperator. But when they won, it seems it doesn't matter how they play. So what's the takeaway message from this study? The outcome of the game had a strong impact on people's perception of the robot and of the team, but positive outcomes seem to forgive or somehow mask selfish behaviors, which can be dangerous. We had 4 follow-up projects on these because this was very interesting to explore. And very briefly, in one of them, we explored if the display of verbal criticism encouraged people to change their selfish actions. In another follow-up work, we explored the evolutionary advantages of selecting cooperative partners only when in a previous game was lost. In a third work, we explored the impact of embodied features. And fourth, we explored the role of agents' transparency. All of these ones were used this game for the record. Okay, now let's dive into the third project, a model of group-based emotions. So in this project, we explored can the expression of group-based emotions by robotic teammate increase the identification and trust? So this means, this is emotional cohesion, right? How much group feelings are expressed. And we took inspiration from this model that says, by introducing the self-categorization step, you could have group-based emotions rather than individual-based emotions. And by introducing this step into an emotional architecture for agents, we were able to produce this type of emotions. And what this step of self-categorization does, in a very simplistic way, it basically, anytime the agent receives a new event, it analyzes who's the actor of this event and if the agent belongs to the same social group of that actor. So if there's any social group where both the agent and the actor of the event belong, it will trigger a group-based emotion. We used the same scenario as in the first project, the card game. And in this case, we had we asked two people, one of them to partner with a robot expressing group-based emotions, and another person to partner with the robot displaying individual-based emotions. This is an example of how the manipulation looked like. So imagine the partner of one of the robots performs a good move in the game. The robot that has individual-based emotions will express admiration and would say something like, "I'm impressed with your move." While the robot expressing group-based emotions, because he identifies with that, within the same group of that partner, would feel pride instead and say something like, "We are the best." So very briefly, the results. The robot that displayed group-based emotions was perceived with higher levels of likability. And in terms of group measures, the teams that had a robot displaying group-based emotions were perceived with higher group identification and higher group trust. So overall, emotional cohesion should be considered in the design of social behaviors for robotic teammates. Another interesting follow-up we had upon this scenario was to explore the stereotype content model in HRI. Okay, finally, the last project, and this one I'm particularly excited about, which was the most recent one. It was done during COVID, so in the previous year. And basically, we explored gaze behaviors in multi-party settings. So we explore this idea of structural cohesion, and in particular, what is a degree of connectivity that a robotic teammate should consider in its perceptive skills. Should a robotic teammate perceive communicative acts only towards itself, or should it also perceive communicative acts between other pairs of team members? And we were inspired by this idea of a silent coordination task. So imagine in some factory, several people need to coordinate in a certain task, but let's say there's a lot of noise and they cannot communicate verbally. They need to rely on nonverbal communication. So in that scenario, we formulated this research question. Are the gaze behaviors of a robotic teammate able to enhance the coordination and fluency of a human-robot team? So we designed these two, or we proposed these two heuristics for gaze behavior in multi-party settings. The attentive gaze, basically, anytime a teammate looks at the robot would return its gaze towards that person. And this is an attempt to establish mutual gaze. Also, anytime a teammate looks at a target that it's not the robot gazes at that target as well. This is an attempt to establish joint attention. And then we have the responding gaze, which performs the same attempt to establish mutual gaze, but it does not perform the attempt to establish joint attention. And instead, whenever a teammate looks at some target that it's not the robot just looks at his screen, looks back at its screen. Okay, so this is how the behavior looks like. Some examples. I'm going to play again. So the human A looks at the robot and then to human B, and the robot will gaze back at human A and then towards human B. And here we have the responding gaze. So the robot does not perform the second gaze as in the attentive. Okay, so what we did was we created 10 scripted interactions for the human behaviors. And then the robot was acting autonomously in 3 different conditions. And one of them was performing responding gazes, on the other attentive gazes, and there was a baseline where in which the robot does not react to perceptions. So we had 30 small videos, and we asked participants in Amazon Mechanical Turk as third persons to evaluate those interactions in terms of perceived teamwork, fluency, coordination, synchronization, work alliance. And the gaze condition was run in a between subjects design. Very briefly, the results we got. So by grouping all the 10 scenes together, we saw that the two experimental conditions can positively affect the perceived fluency of the team, cohesion, and the teammate traits of the robot. However, when we looked specifically at the scenes in which human A gazes at human B, which are the scenes that trigger a different behavior from the robot when it is in the ARGI condition and AGI, what we saw was that attentive gazes were able to improve the perceived fluency of the team. So overall, the takeaway message from this last study was the nonverbal communication structure assumed by the robotic teammate can affect the perception of teamwork. So now the overall conclusion and contribution, I would like to come back to my research problem, which was how can we endow robotic teammates with social capabilities to improve cohesive alliance in a multi-party setting with humans? And we think there were three main contributions. So first, computational mechanisms to develop autonomous social behavior for robotic teammates. And we particularly think we address these in terms of perception, cognition, and also expression. Then the evaluation of people's behavior and perception towards a mixed human-robot group. And those evaluations included objective measures like their collective choices or social-emotional behaviors, and also subjective perceptions of the group, like group identification or group trust. And finally, we contributed with some understanding of relevant group processes in mixed groups of humans and robots, in particular the ones related to cohesion. And finally, to conclude, these are three interesting future directions I would like to point for human-robot teamwork in multi-party. The first one is to analyze different group sizes and human-robot configurations. Even though it seems quite obvious, this one, I think it's really important because of the in-group and out-group biases that might occur. And it's important to test groups where you have more robots than people or more people than robots, for instance. Also, another avenue would be different embodiments and anthropomorphic features, considering the huge variety of robots that are out there with different anthropomorphic features. It's very interesting to see the impact of those. And finally, I think there's a lot of room to improve the autonomous perception of group patterns, especially if our goal is to have intelligent robotic teammates that are able to adapt to what's going on with the group, and perception of those group patterns or group behaviors or group dynamics, it's really important. And that would be all. I would like just to thank all my collaborators in this past 5 years and all the projects I just presented. And yeah, I hope you like it. Thank you.
Thank you very much, Filipa. It was a very good talk and a great topic. And Filipa is on the job market. She'll defend her PhD soon, very soon, we hope. So the floor is open for questions, so please go ahead. Filipa, perhaps I will just ask you to stop sharing your screen so that we go to the gallery mode.
Yes.
Does anyone have a question? Please unmute yourself and go ahead. Yeah, sure, go.
Hello, thank you very much for this presentation. Very interesting. In fact, my interest is also on multi-party conversation, and mostly interesting in what Otsuka calls conversational regimes. So either you are face-to-face, addressing to one person or two persons, or trying to exclude one person from a group and so on. So are you aware of this? Are you monitoring this? Are you interested? Do you take this into account? So especially when you have this card game between four persons, four agents, do you consider this all the possible grouping, in fact, between partners?
Yeah, it's a very interesting question. We have not addressed that, and in particular, the card game scenario, the robot had no perceptions except the events that the robot was receiving from the game. So anytime someone speaks, the robot is not aware. And we tried to address perceptions in this last project, but only in terms of gaze, and it was a very controlled setting. But it's a very interesting question, and as far as I'm aware from the literature, the only person that kind of addressed what you are asking was Marinel Vasquez.
That's basically the work of Otsuka teams. You know, Otsuka is a Japanese guy who has spent almost his whole career on these conversational regimes, studying, of course, human people, but also transferring, building models of the dynamics, in fact, of these gaze patterns, also transferring this to robots. But yeah.
Yeah, we have not addressed those, but as I told you, perception, as I mentioned, in the future direction, sure. It's an issue, and it's a very interesting.
But so in your last experiment, how you detect gaze?
So we used the open face
just
framework.
The open face, okay.
Yeah, just that.
Okay. But are you planning to have, for example, head-eye trackers like KTH, for example? They are using this where every partner has a head-mounted gaze tracker to know precisely where they are looking at.
Well, to be really honest with you, I'm not very fond of those devices. I think they are very intrusive. But my experience using OpenFace was very good, and I think it can fairly reliably detect gaze behaviors, and especially if you can control the possible targets. And
so you have a camera facing the human. So in fact, somehow you constantly the robot doesn't have to move to perceive the gaze of the human partner. So you cheat a bit.
I cheated a little bit, but those cameras are extensions of the robot's perception.
Yeah. Okay. So okay.
There are a lot of challenges in what you are suggesting.
Yeah. Sure. So thank you.
Yeah, Salma, there's a question. Go ahead.
Hello, it's a very interesting research, and I really enjoyed following your presentation and discovering all the experiments that you were able to do. I have a question about the discomfort. I have two questions. The first question about when you talked about discomfort and how the results of the game can have an impact on discomfort. I don't just want to know if you are when you mentioned discomfort, are you talking about the uncanny valley and the feeling of uncanniness? And if it's the case, how the results of the game can reduce these effects?
Okay, thank you for your question. So specifically the discomfort was assessed with the ROSA scale. I don't know if you're familiar with that scale. It was validated for human-robot interactions, and the dimension of discomfort tries to measure discomfort with items like how awful, how unnatural the robot is, and we use that dimension to try to assess how this robotic teammate is being perceived. And in our user study with the For the Record, the selfish robot was indeed perceived as creating more discomfort. But yeah, I'm not sure how it relates to the uncanny valley, in the sense that uncanny valley postulates that the closer appearance becomes to the human behavior or physical shape, the more uncanny you would perceive that robot. In our experiment, it was slightly different, because we are trying to see only if the action they took in the game, like being more pro-social, cooperating, or just by acting selfishly in a selfish way, would cause that discomfort in terms of perception. The robots look exactly the same. So in that sense, we were only trying to see if the action was affecting that perception of discomfort.
Okay, thank you.
Thank you for the
And the
question.
second question is about the design of the robot. Do you expect any different results if you replicate the same experiments with the different designs? Do you think that the fact of having the shape or the anthropomorphic features or the embodiment can impact the results?
Well, so that was one of the follow-up works I mentioned we actually did. So we compared the very first study with For the Record game, and we replicated that experiment on Amazon Mechanical Turk, where people were asked to play the exact same game with two disembodied agents, and they only had speech balloons saying the exact same speech acts than the robots, but they were lacking embodiment, speech, gaze, social presence, physical presence. Well, they had social presence, but not physical presence. And by polarizing these two, so imagine that embodiment is like a spectrum, right? We try to see the two opposite extremes of these dimension of embodiment, let's say, and we found interesting differences. So I would say in the middle of this embodiment spectrum, there would be differences, and it would be interesting to explore what exactly introduces those differences. Is it the speech? Is it the physical presence itself? But our results when comparing disembodied with fully embodied was that in the embodied condition, selfish behaviors were being masked again. So there's something about physical presence and all the social behaviors that a robot can perform that seem to be evaluated in a different way when people are establishing that team with the robots, which is interesting.
Filipa, sorry, Salma, you want to add something?
Just wanted to say thank you.
I'm sorry to
thank you for the question.
So we have a question in the chat from Andrew Stout. I'm not sure, Andrew, if you want to jump in or if I should just read it.
Sure.
I can read it. Oh, okay.
Nice presentation, thank you. I was wondering if you found any instances where the humans' preferences for the robot's personality or behavior are different from what we would expect the human's preference for a human teammate to be, or otherwise surprising results.
So you are referring to the first project, the membership formation, the membership preferences and information, right?
I guess I'm referring more broadly. That one is maybe the clearest example, but also in the cases where, yeah, take it as you will.
Okay, so I think your question is very general, and we can even extrapolate to something even more general, that is the way humans relate with robots similar in any way with the way they relate with humans? And for sure it is similar, but I think there are certainly differences because it's still just a machine, right? And that is what gives purpose to this whole research field of HRI, because we need to keep looking for what is different from interacting with the machine and with the person. And when we design these robotic teammates, we cannot deny, or at least myself, when I designed those interactions, I took a lot of inspiration from the way we want human teammates to be. Even for the card game, for example, when we created the competitive or goal-oriented versus the relationship-driven, it was completely inspired by the way we actually play that game. It's a very well-known game here in Portugal, Sueca. Almost everyone knows how to play. And yeah, but to answer I don't have a straight answer to your question. I think the answer to your question is what the whole field is trying to do, right?
Thank you.
Thank you for the question.
Filipa, I think Naveen wants to ask you a question. If you, you can go ahead, or I can just read it.
Hello, Joanna. I just wanted to ask some question, but it is not somewhat related to presentation. So I believe I should ask my question at the end of the session. So can I ask right now, or should I ask at the end of the session?
Let's wait for the end of the session. Let's see if anyone else has a question for Filipa, so that we discuss more about this topic.
Just to carry on to the follow-up of Andrew's questions. I think it's a key issue because, for example, just the simple presence of a robot in the environment, so what we call social presence, has an impact of the way we take decisions. So we are doing some experiments about this, but in these experiments, what we manipulated is the competence of a robot. So I think it could be very interesting also to examine this. So what are the properties which are somehow transferable to robots, and what could be next? In fact, is perhaps the way. What is the intelligence, in fact, of a robot? It's like, you know, if you are playing a card game, you have a clever or non-clever partner. So it's how to say, it's another dimension, which emotional dimension is very important. But if you are doing some serious game, or you are a co-worker, emotional behavior is important, but competence is very important. Okay, so you have to rely on your partner. So are you planning? Are you interested in manipulating, in fact, this aspect? So competence of a robot, of your partner, regarding the task, in fact.
The only time we actually manipulated that was in one of the works I mentioned as a follow-up, which was the stereotype content model. And those stereotypes that occur in human-human interaction, they basically say, from the perceived competence and warmth you see on someone, you would have different biases or perceptions of that person. And we manipulated that on that study to see if the stereotype applies in human-robot interaction, and it does when the robot actually performs poorer. But it was the only time we actually manipulated the competence of the robot. In all the other works, we were more interested in see if all those social behaviors would be able to create a better team performance rather than the specific performance of the robot.
But for example, if you manipulate this, how to say, if you are competent, you are entitled to be competitive. That's a key question. Okay, so you are more tolerant with incentives and so on. If your partner is highly competent of the task. If it's not highly competent, it will do the reverse somehow. It will, you know, you are non-competent and you complain. You say, you are wrong and so on. So in this case, you know, it's highly modulating. In fact, the opinion you have on the partnership.
The only work where we explored something similar to what you were saying was our paper that is Walk the Talk, that basically we used in the record, the social dilemma.
Yeah. Okay.
We put the robot criticizing the action of the person. So when the person was defecting, the robot would say, "Are you sure you're going to do that?" And we manipulated if that criticism would come from a robot that also was defecting or the one that was being pro-social. But it's hard to map these into the competence on the task, because in that case, it was just a dilemma and they were being more collectivist or more selfish. What you're saying, I don't know any work that explore explicitly that, but it's interesting. It's an interesting idea, yes. Thank you.
This is a very interesting discussion, and I think it could go on and on. I also have a lot of questions, but perhaps we can move the discussion to the Slack channel, and Filipa will answer any other questions that might arise in the future. So to be considerative of everyone's time, I think we should close this session. So let me just share my screen again. And
thank you so much for having me today.
Of course, you have such amazing work. And it was such a nice presentation. And it's good to share it with the community. Okay, so so before we go, I would just like to present. Sorry, so sorry. Wrong keyboard. To present our next speaker, which will be Tesca Fitzgerald. Let me just, I'm so sorry. So apologies for that. So our next session will be in 2 weeks time, and we'll have Tesca Fitzgerald from Carnegie Mellon University, and she'll be talking about human-guided tasks for transfer for interactive robots. So we are moving a little bit of field within HRI, and follow our social media so that you know more details about this talk and the link for registration. So I would like to thank you all. Let's move the discussion to Slack. Thank you very much, Filipa, for presenting your work. Filipa is in the job market, so contact her. She's an amazing researcher.